38. Okay, log problem number 1. The equation that models the time required to reach a particular radiation level after a radioactive leak is given by this equation. Okay, before we go and continue further, right? You know this is a logarithmic. You're going to have a section on your study sheet called logarithmic. You're going to know that 266.44 would be on that graph, right? This value gives it away. It may or may not be helpful, guys. It may or may not be helpful. I'm just telling you, technically this is on the curve, okay? Next, B is negative, right? It's negative 36.36, okay? So what are we expecting? Well, first of all, we're expecting this, something like that. We're going to go in this direction. That's what we expect, okay? So without even graphing, without typing this in, we know a lot of information already, okay? And we're going to do this on a study sheet. I'll help you out with it. Tomorrow, I'll help you out with that. So for now, just try to follow along. So I'm going to go to y equals, clear all that mess, turn off plot 1, because we're not doing a regression here. You go 266.44 minus 36.36. ln. This is what I want to talk about real quick. Calculator here. This is a calculator moment. Please don't mix them up. They're both logarithmics, but if the question has log, press this button. If it has natural log, press that button. As simple as that. Just follow the instructions, okay? But you can't just do whichever one you feel like, okay? So let's press that, ln, and if there, and that's you got to feed it. Oh, what happened there? I went double bracket, so watch out for that. It immediately opens a bracket, so don't be double bracketing because it will give you an issue, most likely. Hit graph. I actually see something, and it is what it's very weird because it looks like it's just coming out of nowhere, right? It looks like it's going to touch my y-axis, but we know better. It doesn't touch the y-axis, okay? Am I going to leave it like this for now? I think for now I'm going to leave it because I'm kind of happy that I see that general shape. It's going towards the x-axis. Is there an x-intercept on this one? Yes? Philbert is saying yes. I believe Philbert. So how about let's chase it till it crosses the x-axis. Let's do that. So I'm going to go x max. That's what I'm honing in on. I'm going to go 250. Go big or go home, right? Still nothing. Let's try 500. Still nothing. So this is going to be a long chase. So I'm going to stop right now. Okay, let's just go back to the problem and see what we can do. So what do we know? T is the time in years. Watch out. Watch out here real. You have to watch for this. This is what throws students off. T is the time in years. Where is T? Over here. What is this normally for us? What variable? X or Y? Y. Okay. And this is X. Got it? So what is time in this context? It's the Y variable. So why don't we go over here and clarify that? It's time in years, so this is my time. And the rest will be what? I is the target radiation intensity. So I'm going to call this radiation. Okay. Did you catch that, guys? Do you know what I'm talking about? All of a sudden, time is my Y. Don't despair. Mr. Dirksen, is it always going to be Y when it's logarithmic? No, it's not always going to be Y. How do you know for sure? Read carefully. You hone in on this variable. You know that is your Y. So then you go look, what is t again? Oh, it's time in years. Well, since it's my y, I'm going to put it over here. Boom. And then the other one has to be this one. It's actually not a big deal. You just have to make sure you read carefully. Logarithmic does mix it up though, okay? The initial radiation intensity after the leak is estimated to be 1,600 millisieverts per year. Millisieverts? I don't know. Make a graph of the time required as a function of radiation target. Let's wait with that a little bit. Hold on to that. Let's do B next. What is the exact initial radiation level according to your equation? Let's do B here. Initial radiation is when? What do we know about time at the very beginning? Is at time equals 0 years, wouldn't you agree? At 0, yeah, that's when we have the initial. So what does that mean? In this case, they're asking me for the radiation level when time is 0. What is this really? What point, what do we call this when y is equal to 0? X-intercept. But even if you didn't know that name, you just know that the y value, y2 is equal to 0, right? When you have the y value, put that into y2, second, trace, intersect. Just read. Let's do that together. So guess what? We're going to have to chase the curve. Okay? There's no way around that. So window, let's go with the X max. I'm gonna go 2000. Okay, I'm gonna stop chasing it and hopefully I find it there. Boom, it worked for me. I see it crossing there when I make X max 2000. So that's pretty good. Now I'm gonna proceed with my steps here. Y2 is equal to 0. Hit graph. And we're going to find that x-intercept. Second trace 5, enter, enter, enter. 1,522.08 if you round it to 2 decimals. X is equal to 1,522.08. And let's use the units that they have. It's MSV per year. I was actually pretty impressed. I did one with fuel economy and speed on the test, polynomials. Remember the linear? You actually, pretty much all of you knew, oh yeah, just use the units that are associated with X, use the units that are associated with Y, no big deal, right? So go like this. All right, good job, good job. All right. That's the initial radiation at time 0. Okay. All right, let's keep going. C. How long is it required to achieve half the initial radiation level? How would we do that? They're basically saying if you take the initial radiation and divide it in half, how long would that take? Does that make sense? What I just did there? Because we know the radiation level. We can figure it out. It's half of the initial radiation. So I have to do the math yet to figure out what it is exactly. But they're asking me for time. Okay? Time is y, so it's kind of weird. But so we're going to go second, trace, value, x is equal to, let's figure out what that is. 1522.08 divided by 2, 761.04. That's what that is. And let's figure out what y is. Second trace 1, 761.04. And it will take 25.20. Make sure you put a 0 there because you are rounding. If it had been exactly 25.2, you don't have to have that. What is our time in? Years. So it'll take 25 years to get to half of what you had initially. And it will take another 25 years to get to half of that, right? So you actually found the half-life. You actually did find the half-life here. The time it takes for your initial, or your previous, I should say, to go down to half. That's what that is. D, what is the radiation level that is reached in 100 years? So they're asking, what's the radiation level when time is 100 years? And since time is your y variable, we let that be y2, and then we go second trace intersect. It probably will require some window adjustments, okay? I'm going to check my window first. Sorry if I'm blocking. I'm going to look to my y max, and that's just fine. My y max is 500, so I can leave it as is. I'm going to go to y equals, turn that into 100, hit graph, boom. So 97.28. That's the radiation in 100 years. And E, I know I'm not graphing, I know that. I think for now I'm just going to focus on you being able to answer questions. If a level of 10 MSV per year is considered safe, how long will it take for the contaminated area to be safe? Again, they're saying when radiation is 10, right? How long will that take to get to 10? So this is second trace value, x is equal to 10. It's 182.72. Years. That's how long it will take for it to be safe. Okay. All right. What are we going to do with the graph? We're just not going to graph this one because I kind of just used up my whole space here. But that's fine. We'll get to it. Can I ask you to, for the rest of today's class, maybe don't focus on the graph. I will post the answer keys. I'm going to ask you to go as far as 42, so 39 to 42. Can I make a sketch though for you guys? Would you be okay if I just did a little sketch for this particular scenario? You don't want a sketch? You can just ignore me, that's fine, okay? But do we care about negatives? We don't care. Listen carefully to this one. Where does time go in this scenario? Yes, time in years goes here. So that's going to throw you off sometimes, but don't worry. If that's what they told you, then that's what you go with. This is radiation. You're going to put the units there for it. Okay? Does it ever touch the y-axis? Does a logarithmic ever touch the y-axis? It doesn't. Okay? So this is what is tricky for a lot of students. They're like, well, I don't know how to go about it. I don't know how to go about it. Do you know your x-intercept? Yes, we do. It's at 1500. So you start there. Find a couple of points along the way. So this is 1500. Maybe find one at 1000. Find one at 500. And then you go like this until it kind of goes up towards the y-axis, okay? This is what the graph, I'm not proud of it, but this is 1522.080, okay? This is the x-intercept. So it all starts at the x-intercept, and then kind of, this one isn't very nice. Like I have to say, you should make sure it has a curve, okay? So that's what the graph should look like. Start with your x-axis and then go towards the y. We're going to practice that a bit more tomorrow. So for today, I just want you to be comfortable with typing it in, finding your window, answering questions. If you want to graph, I'm not going to stop you. I would actually strongly encourage you to graph. I have graphs on the answer keys, so you do that, okay? All right, thank you guys.